Hello, my name is Alexandra Paolino, and this is my Grade 12 Advanced Functions Math CCT. I will be answering question number 13 on page 373. This question demonstrates rates of change in trig functions. This question states, for a certain pendulum, the angle theta shown is given by the equation theta equals 1/5 sine pi over 2t, where t is in seconds and theta is in radians. Part A states, sketch a graph of the function given by the equation. In order to sketch a graph of the function given by the equation, we must first identify the amplitude, type of function, and period. The amplitude is how much the function goes above or below the equation of axis. As identified in the picture, the amplitude is 1/5. The period determines how long the function is on the horizontal or x-axis. It was found by dividing 2 pi by the b value. Therefore, 2 pi divided by pi over 2 equals 4. This is a sketch of the function given by the equation. It is a sine graph as the function begins on the equation of the axis. The vertical axis theta represents radians and the horizontal axis t represents time in seconds. Question B. Calculate the average rate of change in the angle the pendulum swings through in the interval t 0 to 1. The average rate of change, or AROC, is the same thing as the slope of the secant line that passes through the 2 points. In this question, the 2 points that fall on the x-axis are 0 and 1. To solve for AROC, 1 must be subbed into the equation, subtracted by 0 subbed into the equation, all over 1 minus 0. Subbing 1 into the equation equals 0.2, and subbing 0 into the same equation equals 0. I can now sub 0.2 and 0 into my equation. This means that the average rate of change between 0 and 1 second is 0.2 radians per second. C. Estimate the instantaneous rate of change in the angle the pendulum swings through at t equals 1.5 seconds. For a function, the instantaneous rate of change at a point is the same as the slope of the tangent line. In the Advanced Functions course, the instantaneous rate of change is an estimate, as 1/1000th is added and subtracted from the exact value needed to be found. IROC equals 1.501 subbed into the equation minus 1.499 subbed into the equation, all over 1.501 minus 1.499. Through subbing 1.501 and 1.499 into my equation, I now have the numbers I can sub back in to find IROC. Therefore, IROC is approximately negative 0.22 radians per second when t equals 1.5 seconds. D. On the interval t 0 to 8 seconds, estimate the times when the pendulum's speed is the greatest. The speed is the greatest when angle theta in radians is smallest. Angle theta is the smallest at 0. When theta equals 0, t equals 0, 2, 4, 6, and 8. Therefore, the speed is the greatest at 0, 2, 4, 6, and 8 seconds. I will first discuss examples using trigonometric functions. An example where sinusoidal trigonometric graphs are used is to track changes in tides. Tides are affected by gravitational pull of both the moon and the sun. Tides follow a periodic pattern that can be modeled with the sine function. Height and time track the patterns of waves. A wave that has been graphed is shown on the screen. It reaches a height or has a high tide of 9.9 feet and has a low tide of 0.3 feet. Therefore, the amplitude is 4.8 feet. The equation of axis exists at 5.1 feet. Also, the cycle or period takes 12 hours to complete and to return to its beginning height. A second example where sinusoidal graphs can be used is to model fluctuations in temperature data throughout the year. Examples of careers that these two graphs can be used in are for individuals who collect statistics, called statisticians, and environmental engineers. I will now discuss examples involving rates of change. Careers involving rates of change fall under the physical, biological, and social sciences. For example, the speed of a ball falling, or the rate of change in a chemical reaction, or even the rate of decay of a radioactive material. To recap my question, for a certain pendulum, the angle theta shown is given by the equation, where t is in seconds and theta is in radians. I sketched a graph which represent the pendulum. I calculated average rate of change in the angle of the pendulum in the intervals 0 and 1 seconds. I estimated the instantaneous rate of change at 1.5 seconds, and I determined intervals when the pendulum's speed was the greatest.